Welcome to G Fun Facts Online, where we explore the science shaping our future. Imagine trying to build a hypersonic jet, or a power plant that runs hotter and more efficiently than anything before. You'd need materials that can laugh in the face of extreme heat and pressure. For decades, scientists have had the perfect candidates: high-temperature ceramics. These things are incredibly tough, resistant to heat, wear, and corrosion. There's just one huge problem. They're notoriously brittle and have such high melting points that shaping them into complex parts, like a turbine blade, has been incredibly difficult and expensive. It's like having the strongest building material in the world, but it shatters if you try to cut it. But what if you could print it, layer by layer, into any shape you desire? Well, that's no longer science fiction. A groundbreaking technology called Directed Energy Deposition, or DED, is completely changing the game. DED is a super advanced form of 3D printing. Picture a high-precision robotic arm. On its end is a nozzle that sprays a fine powder of ceramic material. At the exact same time, a powerful laser or electron beam melts that powder, fusing it instantly to the layer below. It builds the object from the ground up, molecule by molecule, creating a solid, dense part directly from a digital blueprint. While this tech has been used for metals for a while, applying it to ceramics like zirconia and silicon carbide is a revolution. So why is this such a big deal? First, it gives designers almost unlimited freedom. Traditional methods are clunky and limited to simple shapes. With DED, you can create parts with incredibly complex internal channels and lattices. Think of a heat exchanger with a maze of tiny pathways inside, making it drastically more efficient. This was practically impossible before. Second, it's faster and cheaper. You don't need to create expensive molds or spend ages carving away material. You go straight from a computer design to a finished part, slashing production time and costs. And speaking of carving away material, DED is incredibly sustainable. Traditional manufacturing is subtractive. You start with a big block and cut away everything you don't need, creating a ton of waste. DED is additive. It only uses the exact amount of material required for the part. But here's where it gets really cool. DED can also be used to repair high-value parts. Got a damaged jet engine blade worth thousands of dollars? Instead of replacing it, you can use DED to add new material and fix it perfectly, extending its life. It can even create brand new types of materials. The technology allows you to blend different powders during the printing process. This means you can create what are called functionally graded materials. Imagine a single component that has a super tough metal core that gradually transitions into a heat-resistant ceramic outer shell. This eliminates the weak points you'd normally find where two different materials are joined together. Now, it's not all smooth sailing. The very properties that make ceramics so tough also make them tricky to 3D print. They don't handle sudden temperature changes well. The intense, focused heat from the laser can cause stress and tiny cracks. It's also a challenge to make sure there are no microscopic pores between the printed layers, which could weaken the final part. But researchers are tackling these problems head-on by fine-tuning the process, developing new ceramic powders, and using advanced simulations to get it just right. The potential applications are staggering. In aerospace, DED-printed ceramics could lead to more efficient jet engines and thermal shields for hypersonic vehicles. In the energy sector, it means parts for gas turbines that can run hotter, generating more power with less fuel. It could even be used to print custom medical implants from biocompatible ceramics, designed to be a perfect fit for an individual patient. Directed energy deposition is more than just a new way to make things. It's a key that unlocks the true potential of the most advanced materials on our planet, paving the way for a future of stronger, faster, and more durable technologies that we are only just beginning to imagine.